Variation.
Thank you.
In this section, we're going to look at the idea where as something increases, the other thing no longer increases but decreases. Okay, so they're inversely related, we would say. So instead of saying y equals kx, we're going to write something that's very similar to that, but because they're inversely related, it's going to decrease instead. So think about it this way. If I start with the value, let's say 1/2. What happens if I increase the numerator? If I keep increasing the numerator, what happens to the value overall?
Bigger.
It becomes bigger. Make the numerator 2, make the numerator 3, make the numerator 4. It gets larger. But what happens if I increase the denominator? It gets smaller. So if we want something to get smaller instead of getting bigger, instead of saying y equals kx, what are we going to say?
Y equals K over X.
Y equals k over x. Because what happens now is this. Keep increasing x. Make x bigger and bigger and bigger. Well, that makes the value of y technically smaller and smaller and smaller. Because you're increasing the denominator. When you increase the denominator, the overall fraction itself, which is y, decreases. So this is indirect or inverse variation as opposed to yesterday's, which was y equals kx. That's the only difference in the lesson. Then we're going to also look at the situation where, what if you have something in the numerator and the denominator? Okay, you have like an x1 in the numerator and an x2 in the denominator, or another variable. You'll see on the next slide here. So that's exactly what Niall had stated. Now, another way of representing that, which is common, it really is to see, is the product of two numbers equaling the constant k. So xy equals k is the same thing. And just solve for k, that's what you would get. You would get xy equals k. And look at the graph. Instead of the graph in the previous one, what would the graph look like for y equals kx in yesterday's lesson? What does that graph look like? Yeah, what would y equals kx look like?
Oh, it would look like a straight line going up.
Good. Okay, a straight line that's increasing, going up, increase. Okay, that's y equals kx, but clearly here we're seeing that no longer is there an increase in the graph, but a decrease in the y value. Right, so indirectly related, x is getting bigger and bigger and bigger, but y is getting smaller and smaller and smaller. And that curve nature to it is correct. It's not. It should not be a line. Okay, it's not going to be a line. Y equals k over x has a curve nature to it. And we're going to learn about this curve nature in maybe like 3 or 4 weeks in the last section of the year. They're called rational functions. They could be exponential growth or decay also. I heard you say that. Yeah. But this, for example, in this case, is a rational function actually. But it looks like exponential decay. An example. So if C is inversely proportional to D, and C is 2 when D is 3.6, find C when D is 4.5, and find D when C is 6.4. A very, very common problem for an SAT. Okay, inverse variation. Simply put, okay, nothing like a major word problem, but you still have to know what you're doing. So if C is inversely proportional to D, how do I start? What do I write automatically? Normally we say Y is inversely proportional to X, but now we say C is inversely proportional to D.
I don't have example 1.
Oh no. Does everybody have the same boat right now? Maybe reload the slides. Try to go to Moodle, re-import them. It's possible you accidentally deleted the slide. Yeah. Okay, so what are we going to do here for inverse proportion? What's the equation we're going to write? Okay, y equals k over x, that's inverse variation. In this case, though, I have C is inversely proportional to D. So how can I write it using C and D? And remember, instead of y and x, it's whatever you have.
C equals K over D.
Yep. All right. C equals K over D. Now, at this point in time, what we can do is we can solve for K using this statement right here. Remember, when information is given to you, there's a reason for it. If you're given some values of variables in an equation, usually you're using them to either prove it true or solve for an unknown. Well, the unknown you're solving for is k. So go ahead and solve for k. What do you get for k? Good. And we're not even close to done there. It just gives us the value of k. So we have this general equation right here, and we want to take this k value, plug it in right here, so we can have a specific equation afterwards, specific to this case. So I'm going to write that in red right here. C equals 7.2 over d. I've taken this equation and became this by plugging in k. And now at this point in time, all you're doing is practicing. So come up with what you get for A and B. Okay, find C when D is 4.5, and do it again. Find D when C is 6.4. Remember, when you're given a number, think about where you can plug it in. If you need help, please ask me. Make sense what you did?
Yeah.
Good. Yeah, pretty much everyone. I forgot, because they did the lab.
And what about the, did everything else?
Yeah, is that the lab was 5 points, or was this was 10 points?
I think, did I write 10 in the book or?
Yeah, there was nothing written in the book.
I think I wrote 10. Oh, sorry, you don't mind? I don't mind online.
So it was 10.
I had the 10, yeah. Last one.
Okay.
What do I do if I plug in?
Good guy. So 7.2 divided by 4.5. Yeah.
Okay.
And you'll get 1.6.
Okay.
And then you got what's the other one?
6.4.
So how are you getting C by itself? You're going to flip flop the 6.4 and the C, right? There we go. There we go. All right, quickly, let's plug these in. So we're going to get, in the first case, we're trying to figure out what C is when D is 4.5. So take this value of D, plug it in right here. 7.2 over 4.5 gives us 1.6, okay? Then we want to find out what D is when C is 6.4. So we take C, plug in 6.4 there. So then we have to flip-flop these two. We're going to have 6.4 equals 7.2 over D. So we have to multiply by D, bringing it up, and divide by 6.4, bringing it down. So to switch those positions. 7.2 over 6.4 is 1.125. All right, let's look at an example. That's a word problem. Can you read for us, Charles?
For the cones of equal volume, the height is inversely proportional to the square of the radius of the base. The radius of the cone is 10 centimeters, and the height is 15 centimeters. Find the radius of the second cone of equal volume with the height of 60 centimeters.
So let's make a statement from this. All right, forget the numbers they gave us, but just from the beginning of it. The first thing, the first sentence, that's enough to make a statement. Come up with your own statement. Take like, I don't know, you should be able to do this in 10, 15 seconds. For cones of equal volume, the height is inversely proportional to the square of the radius of the base. Pick variables. You're not given variables right now. You're not given letters, but pick letters.
Would it be h equals k over r squared?
Why is that right? Who can explain? Very good, Charles. Why is that right?
Well, because it says the height is inversely proportional to the radius of the base. So when it's inverse, it has to be in the denominator because the number gets smaller and the other number is going to get bigger.
Good. What one thing did not forget to state? You had it almost all right.
To the square of the
The
base.
square of the radius. You said the radius there. Good. So inversely proportional means put in the denominator. That's it. Since it was the height being inversely proportional to the square of the square of the radius goes in the bottom, the height goes out here, and your constant of proportionality k is still there. Now at this point, what do we do? What do we do next? We have some sort of information, don't we? Mike, help me out. Look at the second sentence. The beginning of the second sentence. How can I utilize that information?
Do you plug in?
Yeah, so what do you do? Go ahead, tell me.
When you plug in the height, 15 centimeters,
All right.
and then the radius.
All right. And then? What can I gain from this?
You can get the value of k.
Very good. So since 10 squared is 100, we multiply this side by 100, it's 1,500, 1,500. As a result, Sabine, what do I have now if I have k? Once I get k, what can I do next?
You can find the radius of the second column.
Very good. So I can do that. What my equation look like, Sabine? Once I have this value, what should I write?
Grade 60 times x squared equals 15.
Good, because we're going to multiply this r squared up is where you're getting the 60 times x squared there. So we'll get r squared equals 1,500 over 60. Cancel these zeros. 150 divided by 6. What's $1.50 divided by 6? 25 cents. Very good. So r is simply 5. Units of, I think it was centimeters.
Yeah.
Why am I not putting plus or minus 5, right? Because then we talk about this in algebra, when you take a square root in an equation, you get plus or minus for them. Why am I not putting plus or minus?
Like you have minus centimeters.
Okay? Displacement can be negative in physics, but an actual radius length cannot be negative. Right? You can move negative displacement, which means you move usually left instead of right. All right, so let's look at something called direct and inverse variation together. It's known as joint variation, but it simply just means you have both of them. So in this case, you have something proportional to one variable, but inversely proportional to another. All right, that's all you have here. So let's look at an example of this. So here we have Newton's law of gravitation says that the force of attraction between two spherical bodies is directly proportional to their masses. Directly proportional to their masses, and inversely proportional to the square of the distance r between their centers. So here's what we have. We've got one mass over here. We've got another mass. Let's make it a smaller mass right over here. The distance from center to center is r, and that should be toward the center. It's a little... Okay? That's the distance r. This is m1. This is m2. There's a force of attraction between any two bodies, like this tissue and this dry erase, whatever it's called. There's actually a force of attraction. The reason it is not really noticed is because their masses are so small, and we're going to see in a minute what the equation looks like. So it's directly proportional to their masses. So what do I start with? The force. Okay, the force is directly proportional to their masses. So how do I write that first? What if it was directly proportional to one of the masses? What would that look like at least?
F equals km.
That would be Km for one of the masses. Good. But if it's both of the masses, how would it change, Charles?
Wouldn't it be square km?
If they were the same, yes. If M1 and M2 are the same, you'd do M squared. But what if they're different?
Well, could you, I'm not sure.
Okay, help out. You're on the right track. You're like almost exactly right. It's not M squared, but
Okay, so k times m1 times m2?
yeah, M1, M2. If M1 and M2 are the same, then it's M squared. That's what I'm getting at. So it's directly proportional to their masses. So usually if it's directly proportional to the first mass, it'd be Km1. If we're directly proportional to the second mass, it'd be Km2. If it's both masses, it's Km1, M2. And if it's inversely proportional to the square of the distance between them, what would that look like? Inversely proportional to the square of the distance between them. Ben, what does inversely proportional mean? Where's it going to go?
In the denominator,
All right. And how do you write the square of the distance?
just put r squared.
R squared. Okay, that's all we have here. So that's what we get for this one. Directly proportional to the masses and inversely proportional to the square of the distance between them. And Newton's law is written that way, but instead of a K, it's a capital G. And it's Newton's universal constant. All right. So I just taught this lesson actually a few weeks ago, or a few days ago rather, right before the last test. This formula has to do with the electric force between two charged particles. And what's interesting is that the nature of the formula is very similar to another formula. So let's go ahead and look at this problem and try to analyze that. So we know that the electric field produced by a charged particle varies directly with the charge on the particle and inversely as the square of the distance from the charge. On a planet galaxies away, the electric field felt at a distance of 13 meters from the charge is 25 newtons per coulomb. When the charge on the particle producing the field is 8 coulombs. The units actually in this case don't really matter, but we can show how they're going to come into play. Determine the charge that will produce a field of 18 newtons per coulomb at a distance of 11 meters. Looks really messy, but it's not that bad. We have to break it down one step at a time. So analyze the first sentence only. Okay, look at the first sentence. What information can I pull from the first sentence? What's important here? Niall, go ahead.
Inversely is the square of the distance from the charge.
All right, so the electric field, and then we see inversely as the square of the distance from the charge. So that means we have another similar setup where we have what in the denominator now? You started with it, so I wanted to see if you could finish it. Inversely as the square to the distance from the charge.
Km squared.
Not km squared, distance. Not m is not distance. You can use many variables, but m would be mass.
D squared.
Yeah. Okay, but if it's inversely proportional, where should that d squared be?
Oh, K over D squared.
Yeah. So we know this is there already. There's always a k up top. Whenever there's any sort of variation, inversely proportional or directly proportional, you have to have a k there. What else? There's one other piece of information we haven't used in the first sentence. Kelly.
The electric field with the charged particle varies directly with the charged particle.
Varies directly with the charge. The charge on a particle in physics is denoted by the letter Q. So where should that Q belong? Where should I write Q? You know? Next to K. All right? Varies directly with the charge, that's KQ. Varies inversely with the distance from the center squared, that's going to be D squared. Now, at this point, use your units. D is a distance, so 13 meters probably goes in for D. Does that make sense? It's easier to know where things go. Or just read the problem. So let's read the second sentence now. The electric field felt at a distance of 13 meters. So right away plug in a 13 here. from a charge. So the electric field felt from a charge is. So the electric field is. So that's going to go in for electric field over here. It's not the charge itself. Okay, it's 25 newtons per coulomb when the charge is 8 coulombs. Okay, so then read the last part of that sentence there. It says, when the charge on the particle producing the field is 8 coulombs. So when the charge is 8 coulombs. So that's what we have here. The charge is 8, that goes in for Q. The distance from the charge is 13 meters, that goes in for D. And the field itself is 25. So you have to break down the sentence and realize what you're actually gaining from each statement. Can we get next? Can we get K, please? Solve for K. Give me to the nearest tenth for K this time.
528.125.
528.
I'm not sure if that's right. I'll check it out.
Let me think. Others? Confirm? Yeah. I have a different number written down, so I'm trying to look at this. I had 528 even for some reason. I don't know why I didn't have a nearest tenth.
What'd you get?
528 point.
125.
Yeah, sorry.
Okay. Yeah, I don't know why I wrote down just 528. Then I wrote down a note to myself. Look at the tenth. I don't know why. All right. I probably had a mistake. So we have the K value now. What kind of an equation can we get from that? What can we get from the value now once we have K? Mike, what equation would I write? Once I have K, what can I do? Right, here's my general equation. I plugged in, I got K. Once I have K, instead of using the general equation, what can I do now?
You don't plug it into the equation.
Yeah, that's exactly right. Plug it into the general equation.
You don't,
I was saying once you have the general equation, right, we started with, we get K, then we want to get the specific equation by doing what you're saying, is plugging it in. So we start by doing this. And then we have to look at that last sentence now. So let's look at that last sentence.
The distance is 11 and E should be 18.
All right, so we know that determine the charge, that means find Q. So looking at this setup over here, we know we're going to be looking for Q. That would produce a field of, so this is the electric field. Field was represented by the capital E. And by the way, you could have used F for field if you wanted to. It just happens to be E, so I just wrote that, but it doesn't matter what variable you use. So the field is 18. The distance is 11. And our goal is to figure out the value of Q. What do you get for Q? 4.1? Let's see. Looks about right. 18 times 121 divided by 528. It's got to be a number greater than 1, that's for sure. Good? Okay, so we understand what we're doing here? The goal every time is the same thing. Plug in your knowns into the general equation. Get the K value every time. Once you get the K value, plug that into the general equation, giving you the specific equation. Then plug in the other information you know to get the unknown value that you're looking for. It's literally the same process every single time. It's the same process we use with direct variation, but now it's just a little bit more complicated. All right, last one. Another one where it's a long word problem, but it's not that difficult. You have to break it down one at a time. Okay, try and read it on your own, and try and underline the important information, and come up with some sort of an equation, just the general equation. So read it very slowly. Okay, break down each sentence one at a time. Yeah, you want to call the spring stiffness S instead of K, that's fine. Call that S, that's fine. Thank you. It is called K in physics, but yeah, since we're using K as our constant variation. Solve for K once you get your setup. Yeah, so just change that. That's what you have to change it. Let me see, go back to your actual one. Yeah, you did the same thing, so. Pair of oscillations of mass radius of harmonic motion is proportional to the square root of the mass. Is that what it's? Not as big, gotcha.
It feels great. Earlier than we thought.
You worked on it ahead of time. Who would have thought?
I sent you the email.
Nice, thank you. Okay, now, one thing I think about is this. But you didn't write the original equation, so you're missing something. So in the original equation, it says it's proportional to the square root of the mass n. So the numerator is going to be that code, and the denominator is going to be that. So I will start by writing the equations first. Alright, so you're good so far, but it's also inversely related to what? And inversely related to the square root of the spring stiffness. Now this K should be mass. So how do you write inversely proportional to the square root? Yeah, call it S. Most of you got the general setup right. Some are still struggling with the K value. I have something mixed up. Let's go over this together. Okay? So we have the period of oscillations of a mass moving in simple harmonic motion. That just means a mass that's vibrating back and forth, okay, which is modeled with a lot of systems and engineering, is proportional to the square root of the mass m. So we start with this right here. What does that tell me? The period of oscillations is directly proportional to the square root of the mass m.
Who's K right color?
Now, and inversely related to the square root of the spring stiffness S.
It would be all K over K radical N would be over radical S.
Very good. So we can put the radical over both of them as one fraction or separately. It doesn't matter, whichever way you want to write it. Now, that's the first part. We need to then look at what's given. the first statement literally says the period of oscillations is 9.2 seconds. So where's that going to go in? P. When the mass is 150, where does that go in? And the spring stiffness is 70. What do we get when we solve for K? 6.28. Now, if we have 6.28 for this one, I'm trying to think of what was troubling people when they were doing the math. What were you guys doing that was incorrect? Yeah. There's a few of you got Ks that weren't 6.28.
I was using the iPad calculator, so I probably.
Okay, use your regular calculator, yeah.
I just didn't swear it.
Okay. That was just that. What about the others? I didn't see 6.28 on many people's, that's why. All right. So let's take a look at this last part now. What mass would produce oscillations of 15 seconds when attached to a spring with a stiffness of 40 newtons per meter? So we have our equation. We're going to have P equals 6.28 radical M over radical S. We know that we're looking for the mass. What mass up here would produce oscillations of 15 seconds? What is 15 seconds? What does that represent? How do you know that? Because it's time. No, that's exactly right. When it's time, the period of oscillations is the time it takes to oscillate back and forth. It's like a pendulum, back and forth. Or a mass on a spring, back and forth. Okay, so the period is 15 seconds. If you didn't know that, look back earlier in the problem. You plugged in 9.2 seconds for the period, right? That went in here. And the units of 9.2 is seconds. So if the units of 15 is seconds, there's a good chance that's also representing the period. All right? Then we're told if it's attached to a spring with a stiffness of 40 newtons per meter. The spring stiffness we defined earlier, right here, as S. So 40 goes in for S next. Before we solve for n, what does this number make you think of? This constant we got. I wanted to point this out. I just thought about it now. This constant k that we came up with.
It's twice the value of pi.
It's twice the value of pi. Approximately, obviously, right? 3.14 is an approximation for pi. This is approximately twice pi. Any idea the reason for that? This is like really outside the box kind of thinking. There is a reason for that. It's not random. It's really kind of weird. And I don't expect you to know, but I just thought I'd ask in case somebody maybe read ahead. Like, not in the book, but just read about this kind of thing.
I guess it's because like springs are circular and like to find like the radius or like the circumference or whatever, you need like pi. So like there's 2 pi.
You're totally on the right track. It's not exactly right, but that's the idea. So springs are modeled by circular motion. When a spring oscillates back and forth, its motion can be determined with a circle. And the circle would actually have the circumference of the circle, not the radius, but the circumference would be 2 pi. A circle with a radius of 1 would have a circumference of 2 pi r, 2 pi times 1. So 2 pi is the circumference of a circle with a radius of 1, and that can be used to model a spring. Okay? To solve for m, we're going to finish up 228. Is that what I got? 228?
3.89.
We'll check. We'll check it tomorrow first thing. Tonight, make sure you work on the homework for 8.2, please. Tomorrow, what can you expect? Quiz tomorrow on 8.1 and 8.2. If you can do one of these ones, like at least one of these with joint variation, you should really be good. Okay, but we have regular, direct, and inverse. Yeah, definitely stick to your regular calculator. Stick to your regular calculator. Just because when you're doing the test, you're going to practice that anyway, you know.
Yeah.
You too, Kevin.